This exercise that we're looking at 9b should be pretty much revision from year 11. So let's get stuck straight into it. Alrighty, so there are some rules for differentiation, especially when you are working out the derivative of x to the power of n, so where you got a positive integer as n. Rule is stated here. Essentially, the power of n goes in front of the x term, and then, or gets multiplied by the number in front of the x, and then we subtract 1 from the power. Yep. So you can see where this is derived using first principles. If you are really keen to investigate that, happy for you to have a read through there to see where it comes from. Alrighty, there are some things that you need to know about the derivative of a polynomial function. Some things that pop up if you are to get the derivative of a constant function, such as f of x equals c, a constant number, then the derivative f dashed x is equal to 0. Everyone should be fairly happy with that. Another thing, if you have a function and it's got a constant out the front of another function, say k multiplied by g of x, then if you had to find the derivative of this here, say f dashed x, it's just the constant value gets pulled out the front, and then you take the derivative of the other function. So in this particular case here, you can see if you had f of x equals 5x squared, 5 is a constant value there that can obviously be pulled out the front, and then you are just finding the derivative of the x squared part, so the other function that's there, which is g of x. So in this case, f dashed x is the same as pulling 5 out at the front and finding the derivative of this g of x part. The derivative of x squared is 2x. Obviously that expands out to 10x there. So that's useful to know as well. Again, if you are working out the sum, say you've got individual functions and they are added together, the derivative f dashed x is just the derivative of each of those parts. Yep, so you find the derivative of this part plus the derivative of this part and so forth. Yep. An example is if you had x squared plus 2x, you'd find the derivative of the x squared, which is 2x, plus the derivative of 2x, which is 2. Similar type of thing with the difference, where you have two functions and you're subtracting them. You find the derivative of each of those and take away the next derivative and so forth and so forth. Alrighty, there's some terminology that you just need to get your head around. What you need to know is that the process of finding the derivative function is called differentiation. That's what we're doing in this chapter here. Cool. So here's the first example. It's asking you to find the derivative of x to the power of 5, take away 2x cubed plus 2. When they're asking you to find the derivative of that, essentially what they're asking is to differentiate the function with respect to x. Cool. So you'd write out the function. Check. What you are then going to do is you are going to follow the rules. So we are multiplying the power by what's in front here. So power is multiplied by 1 in this case, so 5 comes down the front. We take away 1 from the power, which 5 take away 1 becomes 4. Here, what they're doing, now you might know it in a separate way, whereby you're going 3 multiplied by negative 2 is negative 6 and take away 1 from the power. That's cool. They're using the rule that we've just stated before, where you've got the where you got k the constant. So in this case, the constant is negative 2. You've pulled that out, and then you are working out the derivative of x cubed, which is 3x squared, and then you can multiply out the brackets there. Yep. So that's what they're doing there. You might just be comfortable jumping straight to that step there. Here you've got a constant value, a constant function 2. Derivative of that is 0. Cool, happy days. We should move on to the next question. Tick. Worked example number 6. It says here, find the derivative of this one and thus find f dashed 1. So find out what the derivative equates to when 1 is substituted in. So we need to write out the function. Happy days. We're then going to find out what the derivative is using the processes we've had the chat about. Cool. We get the derivative f dashed x is equal to 9x squared, take away 12x. from here, we should be able to substitute in 1 into the derivative to find out what it evaluates to. So 9 multiplied by 1 squared, take away 12 times 1 is -3. Cool. Again, these things can be done on your calculator, and you should be comfortable doing these types of things. So again, they're suggesting you can define a function as f of x, check, and from there we can go ahead and do some of the derivative calculations. So here it says you go to interactive calculation and diff for differentiation, and it will spit out what the derivative is. Yep. It says to find the value of the derivative at, for example, x equals 1. It says tap the stylus at the end of the entry line. So you can go at the end here, select the bar from the Maths 3 keyboard, and then go x equals 1, and it will spit out what the value of the derivative is when x equals 1. Another way you can do it is you can define the derivative as g of x, like they've done there. So set this as the derivative, g of x, and then just substitute 1 into that as follows. Yep, both valid ways there to do that. Next thing, whole idea again with differentiation is it's useful to find the gradient of a tangent line. So it says here, for the curve determined by the rule we've got here, it says find the gradient of the tangent line to the curve at the point 1, -2. So the whole idea is the derivative is going to tell us what is going on at that tangent. First thing we need to do is find out the derivative of this equation. So f dash x, which we can do, check. What we want to do is use this to find out what's happening when x equals 1. Yep. So we're going to substitute 1 into the derivative, and it will tell us what the gradient of the tangent line is at that particular point. In this case, it's -3. So at this point, the gradient of the tangent line is equal to -3. Now, there are different notations that you should be familiar with. Leibniz notation is probably the one that pops up the most. So here, for example, if you have y equals x cubed, then what you can have is the derivative is denoted by, this is pronounced dy dx, and so you would write dy dx is equal to 3x squared. Yep. In particular, dy dx is saying if y is the function of x, then the derivative of y with respect to the derivative with respect to x is denoted by dy dx. So I'll repeat that again. If the y is a function of x, then the derivative of y with respect to x is denoted by dy dx. They can use other letters and things like that. For example, here they've got dz dt. So it's saying if z is a function of t, then the derivative of z with respect to t would be written as dz dt. Cool. Worked example number 8 is just using different letters. Obviously, we're still applying the same process to find out the derivatives, but rather than working out necessarily dy dx, you might be working out dy dt and so forth. So in this case, you still apply the process, but making sure you write out the answers as follows. I reckon you guys should be fairly happy with those. Worked example number 9. Again, before you can work out the derivatives, dy dx, we need to expand these out. Yep. So again, it's a matter of expanding things out and then applying the processes we've had the chat about. Again, I believe each of these is achievable for all of you. There's some other operator notation that you may come across. For example, they could say find the derivative of 2x squared take away 4x with respect to x. It can be written as that there. Yeah, finding the derivative of 2x squared take away 4x with respect to x, like such. So again, they're saying here, when you have this here, it's the same as finding out the derivative, f dash x. Yep. Alrighty, so again, all they're asking here is for you to find out the derivative of each of these with respect to x here, with respect to z, and so forth. Yep, we're still applying the same processes. Alrighty, worked example number 11. It says here, for each of the following curves, find the coordinates of the points on the curve at which the gradient of the tangent line at that point has been given, has the given value. So in this case, we've got an equation. They've also told us what the gradient is. They're asking obviously where these points exist. So what you need to do is, obviously, if you've got y equals x squared, we need to find the derivative of that. In this case, it's 3x squared. We know that the derivative is equal to the gradient. Yep, so in this case, the gradient was equal to 8. We're making the derivative equal to 8. From there, we can solve and find out where those points exist. Obviously here, this one is plus or minus the square root of 8 over 3, which is a surd, which can be simplified down. Yep. B, again, we've got an equation, and the gradient is equal to 0. What we need to do is find out the derivative, which we can. We know the derivative is equal to, in this case, the gradient, which is 0. Rearranging things, and we can find out where that exists. So in this particular case, we find out that it exists when x equals 2, and then you can substitute that back into the original equation to find out its corresponding y value. Yep. I reckon you guys should be fairly happy with that one there. Cool. Again, there's some use on your calculator that I would like you to have a look at, that I believe that you should be able to follow along. Yeah, again, you can achieve this. Have a go at that one. Alrighty, another important thing that sometimes is overlooked is the angle associated with the gradient of a curve at a point. And what it says here is a gradient of a curve at a point is the gradient of the tangent at that point. So a straight line, the tangent associated with each point on the curve. It says here, if alpha is the angle a straight line makes with a positive direction x-axis, then the gradient of that m of the straight line is equal to tan alpha. And here's the equation here for that. The gradient is equal to tan alpha. So again, if you had, for example, an angle, so you had the x-axis, and then you had a line, and you knew that the angle was, say, 45 degrees, you could do tan 45, and it would tell you what the slope of that line is. Oh, sorry, the gradient. Yep, the slope. So it says here, for example, if alpha was equal to 135, then tan alpha equals -1. Yep, so tan 135 is equal to -1, and you get the gradient is -1. Cool, alrighty. It says here, find the coordinates of the point of the curve with the equation y equals x squared, take away 7x plus 8, at which the tangent line does the following. A, makes an angle of 45 degrees with the positive direction of the x-axis. Good news is we already just had a chat about that, yeah? So what you would do is you'd find out the derivative of this equation. Check. We need to know because we know that the angle of 45 degrees with the positive direction of x-axis, we can work out what the slope is, the gradient. It's tan 45, which gives us 1. Okay, so the slope of the graph, or the gradient, should be equal to 1. Yep. So we can make that equal to the derivative. From there, it's a matter of rearranging things to find out where this point is. It happens at x equals 4. And we can substitute that back into the original equation to find its corresponding y coordinate. So it happens at, makes an angle of 45 degrees with the positive direction of the x-axis at 4, -4. Yep. Likewise, doing the same thing, but it's saying is parallel to the line y equals -2x plus 6. Again, what you need to know from this is that the gradient of the line is -2 here. So from here, you can find out the derivative of this, They're finding out when it equals -2, rearranging things. We get 2x equals 5, and therefore it equals x is equal to 5 over 2. You can substitute that back in over here. Cool. Remembering the reason it's parallel to the line y equals -2x plus 6 is they've got the same gradient there. Yeah. Cool. Now, this is what we need to have the chat about here. Last little bit is about increasing and decreasing functions. But in the past, we've had the chat about things being strictly increasing, where an interval, a function f of x is strictly increasing on an interval if x2 is greater than x1, which implies if you've got f of x2, it is going to be greater than f of x1. Likewise, on the other hand, if you've got a function that's strictly decreasing, on an interval if x2 is greater than x1, it implies that f of x2 is less than f of x1. Alrighty, so same sort of thing here relates to the derivative of each of these. So it says here, if f dash x is greater than 0 for all of the x in the interval, then the function is strictly increasing. So it says think of all the tangents at each point, they all have a positive gradient. Yep. On the other hand, if you work out the derivative of f dash x and it's less than 0, so it's a negative value, it says for all the x in the interval, the function will be strictly decreasing. Think of the tangent at each point, they will each have a negative gradient. So this just really says here what is happening at each of these points here, and you can have a read through this, but essentially from here up to this point, it's going to be a positive gradient. Yep. From here down to here, it's going to be a negative gradient. And from here up to here, it's positive again. Yep. So they can ask you these types of things here, like this example. First part is saying, where does the derivative of x, where is it greater than 0? So again, the derivative of 0 is going to be where the graph has a positive slope. Yep. So here, if we're looking at this graph, it's positive in nature from this particular point up to here. So it's going up. So you would say in this particular case, between -1 and 5, so between this point, -1 and between 5 is where it's going up. Yep. Whether you use this notation or this one here, I don't mind. Here it's saying for b, where is the derivative less than 0? So where is it negative? Okay, so it's decreasing, but from here to here, so everything less, also from less from -1, and it's also decreasing from 5 onwards this way. Yep. So again, two different types of notation. You can say it's decreasing when x is less than -1 and union x is greater than 5, so from here to here, or you can write it using this notation as well. Last but not least, it's saying, hey, when is the derivative equal to 0? Basically, you're looking for stationary points where it's changing direction. Obviously, it's changing direction just down here at the minimum, so it's happening at -1, and it's also happening changing direction here at the stationary point at 5. Yep. Cool. Alrighty. So a little bit of information there. Please have a look over the section summary. Good luck with this exercise. Bye for now.